So continuing on from part 2 of the lab with the BJT with the collector feedback bias, here's the 2SC549. Oh look, I probably should say I didn't really plan to do a part 3. But I felt it was necessary because although we looked at the DC parameters and we saw the effects of temperature and the tiny bit of stability offered by the collector feedback circuit, biasing circuit, it was necessary to do a little bit of work on the AC part, whereby I can put a small sine wave, audio frequency sine wave, into the base, capacitively coupled into the base of the 2SC549, and then we can shift the bias by the same way we did in part 2, by changing the resistor in the bias circuit to increase or decrease the current drive to the base, and then see what impact that does have in fact on the on the audio gain, the AC gain of the circuit, and the cue point, where the cue point shifts to on the oscilloscope. Let's first of all then just take away the let's first of all take away the AC signal, and then looking purely at the oscilloscope, let's go into DC coupling, channel 1 coupling, DC coupling on the oscilloscope, and probably if we just disconnect that collector and come down here to give myself a 0 baseline voltage, connect the collector back up again, and then we can see on the oscilloscope that we're up at we're on 1 volt per division, 1, 2, 3, 4, about 4.8 volts. It looks like DC sitting on the collector of that circuit at the moment, and we do have 9 volts of supply voltage. If I put this onto the rail, we'll just jump off the screen momentarily, because 9 volts, we've only got 8 volts of vertical deflection capacity on the oscilloscope. Change the scale to the 2 volt scale, and then 2, 4, 6, 8, 10, 12, 15. Whoops, a daisy, what's going on here? Channel 1, we're on 2 volts per division. Ooh, what's going on here? Goodness gracious, has this thing not gone back to the baseline? That's what's happened. That's pretty weird, isn't it? You'd think from one input voltage to the next that you'd have standardization with where the trace starts from. 2, 4, 6, 8, just a tad over 9 volts. Just out of curiosity, see what happens then if we take that back to 1 volt per division scale. Here's our 2 volts per division, 1 volt per division, and geez, that's like a calibration error on the oscilloscope. Yeah, I had to move that quite a bit to bring the cursor back up to the 0 graticule here. Quite amazing. I don't know whether it's just this particular oscilloscope, or maybe because I haven't run the auto to set it up today, but worth taking note of. Alright, so put the input back on again. Oops, wrong one. Put the input back on again, and we'll bring that back to the collector. 4.6 volts sitting on the collector. And do you recall last time what happened? This has got about 860 k ohms, I think, in the base circuit. And then if we shift that down to about 470k, we've got more current drive going into the base of the transistor now. So we've shifted from that 4.6 volts down to 3.1 volts DC on the collector. Let's have a look at putting some AC waveform into this. Just get that to synchronize nicely there. Look, not sure what the level is I'm putting into the device. I'll have a look at that shortly with the other channel. But at the moment I'm more interested in the symmetry, and knowing that I've got 9 volt rail which is up here. The Q point is set quite low down the low line, and we've got quite a symmetrical waveform that does not appear to have too much distortion. Certainly if I increase the drive from the signal generator there, I still can't see any evidence of too much distortion happening at the top and bottom, until of course we get down here and we get clipping where we've hit ground down here. And of course no clipping on the top because we haven't gone up to rail yet, but if I keep increasing that, we'd get up to rail and we'd have nice square waves appearing. Now that's quite interesting, because if I change the bias to go back to that 860 k ohm resistance, and we've put the Q point now further up the load line, just get some stability happening there. Already I can notice with this small signal that I've got more pointy here and less pointy here. So like I can tell that I've got some degree of distortion happening there. I do not have a perfectly symmetrical waveform. And I'm guessing that if I increase the drive to that, yeah, look, it's much more evident there. I mean, it might not have been evident to everybody's eyes before, but I've got no problems at the top, but got some serious problems happening down here. If we put a distortion analyzer onto that, we'd come up with quite some serious distortion, and audibly that would be quite nasty on the ears. That would be a little bit harsh to be listening to that. So again, that was with probably insufficient base drive to the transistor. By putting the transistor into the middle of the load line. But then if we increase the drive, oh, now look, what I might do there, I might just set the level to give me, let's just call it units, and I'll go to AC coupling for a moment. And what I'm going to be looking at here is just, like I said, if we call these units, and I've got 1, 2, 3, 4 units on the screens, 4 volts peak to peak, say. Then, let's get rid of that. Then, without changing the amplitude of the waveform, let's change the DC bias point. Let's go back to that 470k resistor now. Straight away I can see that I've got a slight difference in the overall gain of the amplifier. I've reduced the gain. Now this is interesting because with AC feedback, that's what we do in fact do. We try and reduce the gain to increase the bandwidth and increase the stability of an amplifier. Here though, I've increased the DC current drive to the base, of the amplifier by just having 470k, shifted the cue point further down the load line, but perhaps I'm working on more of a linear part of the characteristic curves. Now, the definition of a small signal amplifier means that we're only operating on a very small part of the transfer curve. As soon as we try and use a larger part of the curve, we've got a much greater chance of introducing distortion into our waveform. So we've got smaller waveform, but look at this. I can increase the drive right to the point where I got that flat topping there on the 0 volt line, right to that point, and I don't have any appreciable distortion on the waveform. So I'm pretty happy with that. And it goes back to what we said before with the collector feedback bias into the bass, that the cue point will be shifted down the load line. And the AC picture here really does tell a bit of a story. Alright, I think that wraps it up then for the collector feedback bias. This was the part 3 that I didn't intend to make before, but I have gone ahead and made.